Greetings. If you are a person who deeply appreciates winding down at the end of a long day by contemplating the glowing stars, distant planets, and the serene, quiet majesty of the cosmos, then you have arrived at the perfect destination. On this evening's journey, we are completely leaving our familiar home solar system behind us as we gently float out into the deep, velvety blackness that stretches out between the stars. In these profound depths, alien worlds circle around far-off suns, creating a cosmic landscape where practically anything you can imagine becomes possible. Together, we will travel to spectacular worlds where the falling rain is made of molten metal, explore celestial bodies forged entirely from a mixture of ice and burning fire, and observe isolated planetary giants that drift endlessly through the freezing vacuum of space without being anchored to any host star at all. A few of the remarkable things you're about to discover tonight might initially sound like complete impossibilities, but every single one of them is an absolute reality verified by science. If you find yourself enjoying these tranquil voyages through the cosmos, you're always welcome to hit the like button and subscribe to our channel. Doing so truly helps other weary travelers discover their own path to this quiet space as well. For the moment, however, simply focus on getting as comfortable as you possibly can, allowing your physical body to fully relax and letting your heavy thoughts drift away as we begin our journey. Out there in the vastness of space, there are extraordinary planets that experience temperatures far hotter than actual stars. We traditionally know stars as incredibly intense, glowing furnaces of churning plasma that burn at millions of degrees. Yet, believe it or not, there are certain planets that come incredibly close to matching that extreme heat. One remarkable example of this phenomenon is a world known as Kelt 9b, which reaches mind-boggling temperatures exceeding 7,000 degrees Fahrenheit, making its surface significantly hotter than a large number of red dwarf stars in our galaxy. This colossal gas giant circles its massive bright blue host star at such an unimaginably close distance that it manages to complete an entire orbit in just slightly more than a single day. Because of its extreme proximity, the planet is completely tidally locked, which means that one single side of the world permanently faces the blinding sun, absorbing a non-stop brutal onslaught of stellar radiation. The environment is so intensely violent that its upper atmosphere is literally being ripped apart, streaming out into the vacuum of space behind the planet like the glowing tail of a massive comet. This astronomical heat is so intense that normal chemical molecules cannot even hold themselves together, causing them to break apart completely, while heavy metals easily vaporize into gas. It is not merely a hot environment, it represents an extreme state of matter that is beyond any earthly comparison. These ultra-hot Jupiters completely disrupt our traditional understanding of what a planet can be. They fundamentally blur the boundary line that separates a planet from a star, existing as blazing, storm-ravaged infernos that burn brightly for a brief cosmic moment before eventually dissolving into the surrounding darkness. Turning our minds to other possibilities, some exoplanets might be composed almost entirely of solid diamond. While this concept sounds precisely like a concept pulled from a work of science fiction, under the proper cosmic conditions, it is a thoroughly real physical possibility. Certain worlds, particularly those that form in regions of space that are uniquely rich in carbon, can evolve in specific ways that result in a composition made largely of diamond crystalline structures. When a planet develops around a parent star that possesses a significantly higher ratio of carbon relative to oxygen, the raw ingredients available during its early birth naturally lead to the formation of carbon-rich geological features. A prime candidate for this type of world is 55 Cancri e, an exotic super-Earth that is double the physical size of our planet and is believed to contain an absolutely massive concentration of carbon locked under intense pressure. The crushing gravity deep within the heavy interior of this planet would naturally forge vast subterranean regions of pure crystalline diamond. However, it is important to remember that this environment would not glitter or sparkle beautifully in the way we typically envision. There are no fine pieces of jewellery to be found here. Instead, there is only absolute darkness, oppressive heat, and an unimaginable density. Even so, the sheer concept remains completely captivating to the human mind. It is a world entirely forged from the element of carbon, a place where alien mountain ranges may gleam with the hidden light of deeply buried crystal structures, and where geology itself transforms into something otherworldly and precious. Furthermore, there are extraordinary exoplanets that orbit around two suns simultaneously, mirroring the fictional world of Tatooine from Star Wars. In our science fiction stories, humanity has long dreamed of twin sunsets, watching two distinct stars slowly sink beneath the horizon of a faraway world. Today, modern astronomy has confirmed that those exotic skies are not a mere fantasy, but actually exist out in the deep universe. Certain exoplanets do not revolve around an isolated star the way Earth does. Instead, they circle a pair of stars. These are technically classified as circumbinary planets, and they trace beautiful, highly complex geometric loops in space as they dance around pairs of suns that are actively orbiting one another. In scenarios where the two parent stars are locked close together, a planet can circle around both of them seamlessly, as if they were a single gravitational body. On the flip side, if the two stars are positioned much farther apart from one another, the planet might only orbit one of them directly, while being continuously tugged and tilted by the distant gravitational pull of the second sun. This unique arrangement results in a world characterized by highly unusual light cycles, constantly shifting seasons, and the surreal phenomenon of double shadows stretching across the landscape. Although these binary systems are exceptionally rare and structurally delicate, they absolutely exist. Consequently, the sky of a distant world out there is truly illuminated by two dawns and two dusks, proving that a sky once imagined only in fiction has been quietly confirmed by science. In other regions of the galaxy, there are planets where the weather is so severe that it literally rains molten glass. Some worlds are so fundamentally alien to our experiences that even their daily weather patterns completely defy our imagination. Consider the world designated as HD 1897333b, a massive gas giant that is significantly larger than Jupiter. This planet orbits so incredibly close to its parent star that it manages to complete a full circuit around it in just over 2 days. The atmosphere of this world is completely scorching, maintaining relentless temperatures hovering around 700 degrees Fahrenheit. Fierce winds whip around the planet at thousands of miles per hour. Suspended high within its blue, hazy sky are countless microscopic particles of silicate, which are the fundamental chemical building blocks of glass. When the atmospheric conditions align perfectly, these airborne silicate particles condense together and begin to fall from the sky as precipitation. It is not water or ice that falls, but actual liquid glass, which gets swept violently sideways by the high-speed winds screaming through the air. When viewed from a great distance in space, this planet looks deceptively peaceful and displays a colour palette that is strangely similar to Earth. It shows a soft, beautiful blue shimmer as it glows near its sun, but a closer look reveals that it is a violent storm furnace that is utterly uninhabitable. It stands as one of the many exoplanets that serve to remind us that nature's creative imagination extends far beyond the boundaries of our own. In contrast to these arid, scorching infernos, other planets may be completely covered in liquid oceans that extend for thousands of miles deep into their interiors. These specific exoplanets belong to a class known as ocean worlds, which are planets almost entirely blanketed by a global sea. On these unique worlds, there are no continents to be found, and no islands rising above the waves. There are only endless, uniform global waters. These deep aquatic environments are nothing like the oceans of Earth, which only average a few miles in depth. On these alien water worlds, the liquid layer could easily be hundreds or even thousands of miles thick. Right at the surface, the environment might appear calm, shaped by gentle winds, or whipped into massive storms. However, as you descend deep beneath the waves, the physical pressure climbs to unbelievable extremes, eventually creating exotic forms of ice. This is not the typical cold ice we interact with on Earth, but rather a dense, high-pressure ice that is physically forged under the crushing weight of the ocean above. These planets may still possess solid, rocky cores at their absolute centres, hidden away beneath the incomprehensible volume of water. Some of them might even feature liquid layers that are kept warm by internal geothermal heat. Whether or not life could ever emerge and survive in these massive deep oceans remains an open scientific question. Nonetheless, ocean worlds may turn out to be far more common across the galaxy than we previously assumed. They exist as gentle, glistening planets with absolutely no dry land in sight, quietly turning in the darkness of space, far away from any sun we are familiar with. Additionally, many planets are completely tidally locked, meaning that one side of the world always faces toward its star. Not every planet in the universe rotates on its axis in the brisk, balanced manner that Earth does. When a world is tidally locked, one hemisphere is caught in a permanent embrace with its star, while the opposing hemisphere is cast into eternal, unchanging darkness. We actually observe this exact same gravitational phenomenon with our own moon, which is why we only ever see one side of its surface from Earth. However, if you imagine this happening on a massive planetary scale, the consequences are profound. You end up with one entire half of a world being continuously scorched by unending daylight, while the opposite side remains perpetually frozen in absolute night. Directly between these two extreme hemispheres lies a narrow ring-like region, known as the twilight zone. This is a circular band around the planet where the star sits permanently low on the horizon, creating a low-light environment where the temperatures might settle into a range that is just right. Because of this, some planetary scientists believe that under the right circumstances, living organisms could potentially survive within this thin band of cosmic balance. These planets are often subjected to fierce atmospheric winds, unusual cloud formations, and wild extremes in weather, but they are entirely real, and they challenge our core ideas of what truly makes a world habitable. Life, if it ever manages to take root there, might learn to adapt and thrive deep in the shadows, or right along the edge of the light. We also observe massive hot Jupiters that skim so incredibly close to their parent stars that their very atmospheres are boiling off into space. To picture this, think of a planet similar to Jupiter, immense, gaseous, and structurally massive. Now, mentally reposition that giant world much closer to its host star. Bring it so close that it takes mere days to complete a single orbital revolution, and where the local temperatures skyrocket well beyond 2000 degrees. These are the hot Jupiters, giant gaseous worlds that skim just above the blazing surface of their stars. They are so close to the stellar fire that their upper atmospheric layers are literally being cooked and blown away into the void of space. Over the years, astronomers have discovered a vast number of these bizarre worlds, and they were actually among the very first exoplanets humanity ever detected. Their massive physical profiles and exceptionally tight orbits make them much easier to spot with our instruments, yet they remain deeply mysterious to science. How did such colossally heavy planets ever manage to end up so close to their host suns? Did they originally form in those scorching positions? Or were they slowly pushed inward over long periods of time by complex gravitational forces? Some of these planets trail glowing plumes of gas behind them, making them look like giant comets. Others are gradually shrinking as their atmospheres continuously evaporate away. They are unstable, highly dramatic, and often short-lived worlds, brief flashes of planetary fire circling around distant suns. In stark contrast to those bright, evaporating infernos, some exoplanets are physically darker than charcoal. Not every planet reflects starlight efficiently the way Earth or Venus does. There are worlds that absorb almost every single photon of light that strikes them, making them darker than paint, darker than ash, and darker even than a block of charcoal. A prominent example of this dark phenomenon is a world called Tris 2b, a gas giant that orbits a star located roughly 700 light-years away from us. The specialized atmosphere of this planet reflects less than 1% of the visible starlight that hits it. To this day, scientists are not completely certain what chemical processes cause this extreme darkness. It could potentially be driven by the presence of vaporized alkali metals, or perhaps completely unknown chemical compounds floating within its upper atmospheric layers. Whatever the underlying cause may be, the physical result is extraordinary. A planet as dark as coal, glowing with a faint, eerie heat, and remaining nearly invisible in reflected starlight. Even its night side, which is already turned away from the star, is only slightly cooler than its daytime side. If you could somehow stand in nearby space and look directly toward it, you would likely only perceive a faint silhouette cast against the brilliant fire of its parent star. It exists as a nearly perfect shadow, orbiting in complete silence and absorbing the light of the universe. Furthermore, astronomers have discovered planets floating completely alone through the cosmos, without a star to call home. While most planets we know are bound to stars, this is by no means a universal rule. Some worlds are true cosmic wanderers, free-floating planets that drift through the interstellar void entirely alone, unbound by the gravitational chains of any sun. These are scientifically designated as rogue planets, and our instruments have uncovered evidence of dozens, or perhaps even hundreds of them scattered across our galaxy. They may have originally formed in a normal planetary system, only to be violently ejected out into deep space later on, due to gravitational disruptions caused by neighbouring planets or passing stars. Alternatively, they might have formed in complete isolation from the start, developing much like failed stars that simply never managed to gather enough raw mass to ignite nuclear fusion. Because they lack a star, these worlds are dark, intensely cold, and exceptionally difficult for astronomers to detect. However, by utilizing highly powerful infrared telescopes, we can occasionally catch subtle hints of their faint thermal glow. Some of these lone worlds might still preserve a degree of internal geothermal heat, which could potentially keep subsurface oceans warm for billions of years. Others might be completely frozen solid, drifting forever through the absolute blackness of the galaxy. It is a world without a sunrise, a planet with no sky. And yet, even in these lonely environments, the quiet question persists. Could some form of life manage to exist in such absolute stillness? In other parts of the galaxy, certain worlds may feature clouds made of ruby and sapphire. When we think of clouds on Earth, our minds naturally imagine water vapour, soft, pale, and constantly shifting across the sky. But on some exoplanets, the high-altitude skies may literally shimmer with liquefied gemstones. On scorching hot gas giants where the temperatures regularly soar well above 2,000 degrees, minerals that would exist as solid rock on Earth can easily vaporize. These vaporized minerals rise high into the atmosphere, where they condense into exotic clouds. These clouds can be composed of aluminum oxide, iron, titanium, and in certain unique instances corundum, which is the exact mineral form that creates rubies and sapphires. These heavy mineral clouds likely scatter incoming starlight in highly unusual ways, tinting the alien skies in shades of deep red, brilliant purple, or profound blue. On one such world, known as HAT P7b, researchers have observed shifting dynamic patterns in the atmosphere. These patterns strongly suggest that high-altitude mineral clouds are actively sweeping across the alien sky. It is truly difficult for the human mind to fully picture a world wrapped in extreme heat and violent storms, illuminated by a blazing sun, while clouds of liquid gems glint and swirl overhead. The universe is continuously proving to be far stranger and more beautiful than we can easily imagine. Additionally, there are super-Earths that could potentially be far more habitable than our own Earth. Some exoplanets fall into a specific structural category known as super-Earths, which are defined as rocky planets that are physically larger than Earth, but smaller than the ice giant Neptune. Because of their larger size, they can possess stronger surface gravity, thicker atmospheres, and highly stable global climates. Remarkably, some of these worlds may actually be even more hospitable to the long-term evolution of life than our home planet. One such candidate is Kepler 4142b, a rocky planet situated comfortably within the habitable zone of its parent star. In this ideal orbital position, it is not too hot and not too cold, receiving just the right amount of starlight. Furthermore, it possesses the necessary physical mass to securely hold onto its atmosphere and maintain liquid water on its surface. Some super-Earths could feature much deeper oceans, far fewer destructive tectonic disruptions, and a greater overall level of surface stability over billions of years. All of these favourable environmental conditions could significantly help life successfully emerge and endure. Of course, we do not yet know for certain if any of these planets truly harbour life, but they serve to remind us of something deeply humbling. Earth may not actually be the absolute perfect planet in the universe, but simply the one we happen to call home. We have also discovered planets that complete their entire orbits in just a few hours. Most planets we are familiar with take several months or even multiple years to complete a single trip around their star. Earth takes a full year, while Mercury, the swiftest planet inside our own solar system, takes 88 days. However, certain exoplanets move at a much faster pace. We have uncovered worlds that race around their stars in a mere matter of hours. One of the absolute fastest known is Kepler 78b, a planet that is just slightly larger in size than Earth. This world completes a full orbit every 8.5 hours. It is positioned so close to its parent star that its entire surface is highly likely a churning desert of molten rock. Temperatures there regularly reach several thousand degrees. These ultra-short period planets are almost always tidally locked, meaning their days and nights are permanently frozen in place. From the surface, their host stars would loom colossally huge in the sky. The intense stellar gravity pulls violently at their internal structures, and some of these worlds may be in the slow process of being torn apart completely. These planets are extreme, fast, hot, and highly fleeting, yet they exist, skimming the outer edges of their stars like bright sparks flying from a flame. Conversely, other planets take entire centuries to finish a single orbit. While some exoplanets race around their suns in a few hours, others prefer to take their time, embarking on long, silent journeys that can last for hundreds of years. One of the slowest moving worlds discovered to date is GU Piscium b, a massive gas giant that requires roughly 1,000 years to complete just one orbit around its star. Its orbital path is so incredibly distant that it is barely held in place by the star's gravity. If it were positioned even a fraction farther away, it might break free from its star entirely and drift into deep space. These long-period planets are exceptionally difficult for astronomers to detect. We obviously cannot afford to wait 1,000 years to watch them complete a single loop. Instead, we must catch them in motion, identifying a slightly curved path, a long geometric arc, or a subtle hint of something vast moving through the dark. Some of these distant planets may possess cold, dark surfaces that are illuminated only faintly by distant starlight. Others may experience seasonal shifts that last for entire human lifetimes. On such cold, far-off worlds, the passage of time and change is measured not in years but in generations, a slow and silent rhythm that exists far beyond our own. To date, humanity has successfully discovered thousands of planets existing far beyond our solar system. For the vast majority of human history, our species only knew of one single planetary system, our own. We were only aware of the sun, the moon, and the wandering stars that drifted across our night sky. However, everything fundamentally changed in the 1990s when the very first exoplanets were officially confirmed by astronomers. Today, thanks to advanced space telescopes like Kepler and TS, we have successfully located thousands of planets orbiting around distant suns. Some of these are small, rocky, and remarkably Earth-like, while others are massive gas giants that are entirely strange to us. Some orbit their stars tightly in just a few days, while others take centuries to complete a single trip around their sun. Every single new discovery we make serves to reshape our understanding of what is possible in the cosmos, and still, this is merely the opening chapter of our exploration. We currently estimate that there are hundreds of billions of planets waiting to be found in our galaxy alone. In fact, there are likely more planets than there are stars, creating a universe of worlds upon worlds quietly orbiting in the dark. We will never possess the ability to physically reach the vast majority of them, but we can listen for them from afar, measure the shadows they cast, and wonder what else might be waiting out there in the deep. One of the primary ways we detect these planets is by observing the tiny shadows they cast during transits. The light shining from a star is usually completely steady, but occasionally for a brief period it dims slightly, creating a tiny dip or a momentary flicker in brightness. That subtle dimming often signifies that a planet has passed directly in front of the star from our perspective. This technique is known as the transit method, and it has proven to be one of the most powerful and reliable tools we possess for locating exoplanets. When an alien world crosses the face of its star from our point of view, it casts a faint shadow. This is not done in the dramatic, blinding way we experience during a total solar eclipse, but rather as a subtle, minute drop in overall brightness that is often less than 1%. Specialized space telescopes like Kepler and TESS have masterfully utilized this technique to uncover thousands of exoplanets. From analyzing just those brief shadows, scientists can accurately calculate a planet's physical size, its orbital path, and even gather subtle hints regarding the chemical composition of its atmosphere. We're essentially watching distant stars blink ever so slightly to learn the secrets of unseen worlds. It is the light of a distant sun, briefly interrupted by the quiet silhouette of a planet crossing far away. Other worlds have been successfully located by detecting the subtle gravitational wobble they induce in their parent stars. Even a planet's gravity can leave a clear fingerprint on its star. When a planet orbits a star, it does not simply move around a perfectly stationary object. Instead, its own gravitational pull causes the star to move in a tiny circle, or wobble slightly as well. While this wobble is exceptionally small, it is completely real and measurable. As the star shifts gently back and forth in space, the starlight it emits shifts along with it, becoming slightly squeezed and stretched by the motion. Astronomers can detect these minute changes by using the science of spectroscopy, breaking the incoming starlight down into its individual color components and searching for the subtle, telltale signatures of movement. This approach is technically called the radial velocity method, and it was the historical technique used to discover the very first exoplanets. It functions most effectively for locating massive planets that orbit close to their stars, such as hot Jupiters, but it has also helped us map out multi-planet systems and identify worlds with long-period orbits. In these cases, we're not viewing the planets directly, but rather watching their stars sway under their gravitational pull, like a dance that is too distant to see, but close enough to feel in the music of the light. Furthermore, we're beginning to observe that certain exoplanets appear to have entire atmospheres that are actively escaping out into space. A planet's atmosphere is never truly still or completely locked in place. Winds constantly blow across landscapes, clouds drift over horizons, and tiny atmospheric particles gradually manage to escape. But in some truly extreme and dramatic cosmic cases, the entire upper atmosphere of a world may be drifting away en masse, leaking directly into the freezing space vacuum like a faint breath disappearing into the absolute void. This specific environmental phenomenon is especially common in exceptionally hot close-in gas giants, where the intense non-stop radiation pouring out from the nearby star can heat the outer gas layers until they rapidly reach escape velocity. These planets can eventually develop long, glowing, comet-like tails of escaping hydrogen and helium gas stretching out behind them. We have actively witnessed this process occurring in several exoplanets, where specialized ultraviolet light observations reveal long, trailing plumes of gas streaming far behind them as they orbit. Some planets may lose a highly significant percentage of their total mass this way over vast stretches of time. Others might eventually be stripped down completely to their heavy, solid, rocky cores. This violent process plays a major role in helping to shape the overall evolution of planetary systems, clearly demonstrating how active stars can sculpt, reshape, or even completely destroy their planets over time. It stands as a profound reminder that even massive worlds can change, erode, and fade away, leaving only their quiet gravity behind. In other areas of our galaxy, we have successfully found planets existing in star systems that feature 3 or even more suns simultaneously. Not every single star system in the deep universe is structured like our own familiar neighbourhood. Some systems contain not just one isolated star, but rather 2, 3, or even more distinct stars, all orbiting together in a complex gravitational dance. And in a few of these highly complex multi-star systems, our instruments have successfully detected the presence of actual planets. Imagine standing on a world where the sky above is never fully dark, a place where physical shadows continuously stretch out in completely different directions across the ground, and where one bright sun may be rising in the east, while another separate sun is slowly setting in the west. These unique planets must follow highly delicate, remarkably stable orbital paths just to survive the tangled, competing gravitational pull of multiple massive stars. Some of them orbit closely around a tightly bound pair of central stars, functioning as circumbinary planets, while others orbit far beyond the entire stellar cluster, tracing incredibly wide, sweeping loops around a highly chaotic centre of gravity. The lighting on such worlds would be exceptionally strange. The natural seasons would be completely unpredictable, and the sky would remain constantly full of celestial motion. Yet, these planets absolutely exist, and they remind us that planetary systems can form in ways we never expected, even in places where gravity is complicated and the night sky never settles. Planets simply find a way. Looking even deeper into the cosmic graveyard, some worlds orbit the collapsed, cold remains of dead stars. Stars do not live forever. Some eventually end their long lives as white dwarfs, which are small, intensely dense remnants of stars that once looked much like our own sun. Others violently collapse into hyperdense neutron stars, or even morph into black holes. And around some of these ancient stellar corpses, astronomers have successfully located planets. These lonely worlds orbit what remains after a star has died, circling glowing embers or pulsing remnants of ancient stellar fury. In some instances, these planets are true survivors, somehow managing to endure the chaotic, destructive explosion of a supernova. In other scenarios, they may have actually formed completely from the leftover debris field that remained behind, rising directly from the cosmic ashes into something entirely new. The light emitting from these dead stars is incredibly dim, cold, or highly distorted. But the planets remain nonetheless, tracing silent, predictable paths through a kind of haunting stellar graveyard. Some are continuously blasted by intense radiation. Others drift quietly, circling dead suns in an unchanging eternal twilight. It is an environment that is deeply haunting and beautiful, a stark reminder that even after the absolute end of a solar system, something new and strange may begin again. In addition to these bizarre orbits, one specific planet actually orbits its star backwards. The vast majority of planets in the universe orbit in the exact same direction that their parent star spins. That is how solar systems traditionally form, emerging from a single, uniformly swirling disk of raw gas and dust. But nature does not always follow our structured rules. We have discovered at least one exoplanet, designated as WASP-17b, that orbits its star in the completely opposite direction. Instead of moving in harmony with the star's natural rotation, it actively pushes against it. This backwards orbit likely formed through a history of immense chaos, perhaps a near-miss collision with another world, a massive gravitational shove from a passing star, or some other violent rearrangement that occurred long ago. This planet is massive, incredibly bloated, and blisteringly hot, orbiting close to its star every few days. The fact that it moves in reverse severely challenges our core understanding of how planetary systems evolve, and it proves something incredibly important. The universe is far more flexible, more chaotic, and more surprising than any single human theory. Some planets follow the flow, others push directly against it, and some, like this one, move through the cosmos with quiet defiance. Furthermore, we have seen definitive signs of clouds existing on planets that are located many light-years away from us. It may seem completely impossible, but we have successfully detected signs of clouds on exoplanets dozens, even hundreds of light-years away. This is not accomplished by seeing them directly with our eyes, but by carefully studying the precise way starlight passes through a planet's atmosphere during a transit event. As the star's light filters through the outer edge of an alien world, some specific wavelengths of light are absorbed while others pass through or scatter away. This delicate, colourful fingerprint tells us exactly about the gases, molecules, and microscopic particles suspended in the air. In several distinct cases, the data suggests the clear presence of clouds. These are not white, cottony water clouds like we have on Earth, but rather dark, metallic or mineral-based clouds made from silicate, iron, or other exotic chemicals. These heavy clouds can reflect or block starlight, heavily shaping the planet's overall appearance and surface temperature. Some planets are permanently cloud-covered, while others show constantly changing patterns across their skies. We cannot yet view these worlds directly, but we can read their weather from starlight alone. In stark contrast to our own solar system, some exoplanets orbit significantly closer to their parent stars than Mercury does to our Sun. Mercury is already a scorching, extreme world, serving as the closest planet to our Sun, completely bathed in intense light and heavily stripped of its atmosphere. But some exoplanets orbit much closer to their stars, at distances where absolutely no planet in our solar system could survive. These extreme worlds complete their entire orbits in mere hours or days. Their surfaces may be completely molten, and their atmospheres are continuously whipped away by brutal stellar winds. Some are completely tidally locked, with one side blistering in unending daylight, and the other frozen in eternal darkness. Others are positioned so close that they literally bulge from intense tidal forces, stretched like teardrops by their star's immense gravity. These extreme planets challenge our core ideas of habitability, yet they are among the easiest for us to detect thanks to their short orbital periods. Many of the first exoplanets discovered were in this category. They are hot and often unstable, but they show us just how flexible and extreme planetary systems can be. Conversely, other worlds drift far beyond the reach of any meaningful sunlight. Not all planets huddle close to their stars. Some orbit so far away that sunlight becomes a faint, feeble glow in the night. These distant worlds may take hundreds or even thousands of years to complete a single orbit around their host. In these outer reaches, temperatures plummet dramatically. Seasons can span entire human generations, and in the deepest cold, chemical reactions can slow down to a crawl. Yet even here, planets persist, silent and slow, circling their stars at the very edges of gravity's reach. Some may be icy giants wrapped in deeply frozen clouds. Others could be rocky and barren, crusted over with thick ice and carbon dust. And some may have hidden warmth beneath the surface, sustained by radioactive decay or ancient heat trapped from formation. These far-flung orbits are hard to detect, but their existence reminds us that planets can survive in places we once thought empty. Even in the loneliest reaches of space, a world can quietly endure. There are also planets with spectacular hypothetical ring systems that put Saturn to shame. Saturn's rings are beautiful, delicate bands of ice and dust suspended around a gas giant. But they may not be the most impressive rings in the universe. Some exoplanets appear to have rings that are thousands of times larger, stretching across vast distances, wide enough to eclipse their host stars. One candidate is J147b, a giant planet or brown dwarf that may be surrounded by a ring system over 200 times larger than Saturn's. These rings could be made of ice, rock, or dust, possibly representing the remnants of forming moons. As the planet orbits, its rings may cast deep shadows on the star, creating strange dips in light that we can detect from Earth. If such a planet were placed in our solar system, its rings would stretch across the night sky. They are hypothetical for now, but their shadowy presence hints at the grandeur still waiting to be confirmed. We've only just begun to scratch the surface. For all we've learned about exoplanets, we're still at the very beginning. The first confirmed discovery was made in 1992. In cosmic terms, that's barely a heartbeat ago. Since then, technology has leapt forward. Thousands of planets have been found, and thousands more await confirmation. We've detected atmospheres, measured sizes and orbits, and mapped their skies in light and shadow. But we've barely begun to understand what these worlds are truly like. We can't yet see their surfaces. We don't know what they smell like, sound like, or feel like underfoot. We can't say which ones have clouds, continents, or creatures. The truth is, every new exoplanet we discover is a doorway to something we've never seen. And as our tools grow sharper, the picture will only grow stranger, richer, and more full of wonder. The cosmos is full of planets, and we've only just knocked on the door. Some planets orbit so close they're slowly being vaporized. For some exoplanets, being close to a star is more than just hot, it's destructive. These planets orbit so near their suns that the intense radiation and stellar winds begin to strip them apart. The outer layers of their atmospheres heat up, expand, and gradually evaporate into space. Some form long glowing tails of gas that stretch behind them like comets caught in eternal retreat. Over time, these worlds lose mass, slowly shrinking, thinning, or transforming entirely. One planet, KC-12FAM-7548b, may be crumbling under this kind of erosion. Its surface is shedding dust and debris with each orbit. It's like watching a planet dissolve in slow motion. These aren't just places to live. They're dynamic systems constantly reshaped by their environment. Even something as vast as a planet can be worn away little by the unrelenting light of a star. We've discovered worlds that defy all expectations. Every time we think we understand planets, the universe hands us something we can't explain. We found planets where the skies shimmer with vaporized metal. We found rocky worlds hotter than lava, and giant gas planets colder than deep space. We've seen worlds with tilted orbits, backward spins, and rings so large they could block out a star. Some planets are too dense, others are too fluffy. Some shouldn't exist at all, at least not according to our models. But they do. Each strange discovery forces us to rethink how planets form, how they evolve, and what might be possible. Science thrives on these surprises. In the chaos of the cosmos, order is only part of the story. The rest is made of exceptions, edge cases, and quiet contradictions. Little cosmic puzzles scattered through space, waiting for someone to notice them and wonder. Some exoplanets might be water worlds with no land at all. Imagine a planet with no continents, no islands, no shorelines, just endless oceans stretching in every direction. These are water worlds, exoplanets where the surface may be completely covered by liquid water. Not shallow seas like Earth's, but oceans hundreds or even thousands of miles deep. Beneath the surface, the pressure would be intense, enough to compress water into exotic ices and crush rock into unfamiliar forms. Some of these worlds might have atmospheres rich in steam or clouds of vapor circling overhead. Others could be wrapped in hazy mists, warmed by sunlight or internal heat. If life exists on these planets, it would evolve in a deep, sunless sea shaped by currents and chemistry rather than light. We haven't yet seen the shores of these global oceans, but their existence reminds us that liquid water, the fundamental ingredient for life, can exist in quantities far greater than we ever imagined. Furthermore, we're uncovering evidence that certain giant planets might actually have hidden rocky cores that are slowly dissolving into liquid metal deep within their interiors. For a very long period of time, planetary scientists simply imagined gas giants as being neatly and crisply divided into distinct layers, featuring a massive outer envelope of gas surrounding a perfectly solid, icy or rocky core at the absolute centre. But modern space observations and advanced gravitational measurements have completely overturned this traditional viewpoint. On exceptionally massive gas giants that sit very close to their host suns, the internal pressures and temperatures reach such extreme, mind-boggling limits that the boundaries between states of matter break down entirely. Under the crushing weight of thousands of miles of heavy atmosphere, hydrogen gas transforms into a dense glowing fluid that conducts electricity like a metal, known as liquid metallic hydrogen. This churning, hyperheated metallic ocean sloshes directly against the planet's central rocky core for billions of years. Over immense stretches of time, this intense heat and pressure cause the heavy elements of the core, such as iron and rock, to gradually dissolve and diffuse upward into the liquid hydrogen layers. This creates a highly unusual, spread out or fuzzy core that spans a huge percentage of the planet's total interior volume, rather than a sharp, solid sphere. This remarkable process changes our understanding of how giant worlds evolve over time, showing us that a planet's deep interior is not a static, unchanging monument, but a slowly mixing chemical furnace that continuously alters its own internal architecture. In addition to these dissolving interiors, we are discovering that certain exoplanets possess magnetic fields that are vastly more powerful than anything we observe inside our own solar system. A planetary magnetic field is an incredibly vital component of a world's overall anatomy, acting as an invisible shield that protects the planet from the harsh radiation of space and shapes its atmospheric weather. On Earth, our magnetic field is generated by the churning of liquid iron deep within our molten outer core. While it is strong enough to guide our compasses and create beautiful auroras at the poles, it is completely dwarfed by the fields generated by massive exoplanets. On giant worlds that spin rapidly on their axes and possess vast interiors filled with liquid metallic hydrogen or salty oceans, the internal electrical generators are absolutely colossal. These worlds can produce magnetospheres that stretch across millions of miles of space, trapping high-energy particles from their host stars and accelerating them to nearly the speed of light. If you could somehow see these immense magnetic fields with your naked eyes from Earth, they would appear many times larger in the night sky than our full moon, glowing as massive invisible structures dominating the darkness. These intense magnetic environments create relentless, powerful auroras that blast out high-energy radio signals, which astronomers can detect from light years away. They serve as a clear reminder that the most influential forces shaping a planet are often completely invisible to our eyes, working silently in the dark to govern the space around them. Turning our attention to more temperate environments, astronomers have successfully located planets orbiting within the habitable zones of cool red dwarf stars. Red dwarfs are the absolute most common type of star in our galaxy, accounting for roughly 3/4 of the entire stellar population in the Milky Way. These stars are significantly smaller and much cooler than our own yellow sun, burning their nuclear fuel at a very slow, stable pace that allows them to live for trillions of years. Because they emit far less heat and light, their habitable zones, the orbital region where liquid water can theoretically exist on a planet's surface, are positioned exceptionally close to the star. A planet residing in this zone must orbit its red dwarf at a distance that is often much closer than Mercury is to our Sun, completing a full revolution in just a couple of weeks or even a few days. This tight proximity means these worlds are highly susceptible to being tidally locked, facing one side toward the stellar fire forever. They're also frequently subjected to powerful stellar flares, as young red dwarf stars can be incredibly active and violent, blasting out intense bursts of X-ray and ultraviolet radiation that can strip away a planet's air. Yet, because these stars live for so long, any planet that manages to successfully hold onto its atmosphere and water has an incredibly vast stretch of time for life to potentially emerge and adapt. These systems represent an entirely different style of solar system, where the sun looms large and red in the sky, and time itself stretches out almost indefinitely. Furthermore, we are finding that a large number of these rocky worlds orbiting red dwarf stars may be completely devoid of any atmosphere whatsoever. When a planet orbits exceptionally close to its parent star, it is constantly engaged in a brutal, invisible tug-of-war to preserve its air against the unrelenting power of the stellar wind. In the case of rocky planets orbiting active red dwarf stars, the non-stop onslaught of high-energy radiation and charged particles can act like a cosmic sandblaster, slowly but surely chipping away at the gas molecules in the planet's upper atmosphere over hundreds of millions of years. If the planet does not possess a powerful global magnetic field to deflect these particles, or if it lacks active volcanic systems to continuously replenish the lost gases from its interior, its atmosphere will eventually be completely stripped away into the vacuum of space. This leaves behind a bare, naked ball of rock that is directly exposed to the freezing cold and harsh radiation of open space, much like our own airless moon or the planet Mercury. Without an atmosphere to distribute heat around the globe, these worlds experience extreme temperature swings, with the day side baking in intense heat, while the night side plummets into the deep freeze of absolute zero. These barren worlds stand as a sobering reminder of how fragile a planet's habitability truly is, showing us that simply being in the right orbital position is not always enough to guarantee a welcoming environment. In contrast to those airless naked rocks, some exoplanets are wrapped in atmospheres that are so incredibly thick and dense that they create an oppressive global greenhouse effect. These worlds are often described as super Venuses, sharing many of the same hellish environmental characteristics as the second planet from our Sun, but on a much vaster scale. Imagine a rocky world that is significantly larger and heavier than Earth, possessing an immense gravitational pull that allows it to capture and securely hold onto an enormous blanket of carbon dioxide, sulfur dioxide, and other heavy greenhouse gases. The atmospheric pressure at the surface of such a world would be completely crushing, equivalent to the intense pressure found deep at the bottom of Earth's oceans, easily enough to flatten a heavy metal spacecraft in an instant. This dense air acts like a heavy thermal blanket, trapping every single bit of incoming starlight and preventing heat from escaping back into space. As a result, the surface temperatures skyrocket to incredible extremes, remaining uniformly hot across the entire planet, from the equator to the poles and through the day and night. The landscapes of these worlds are likely shrouded in an unchanging dim orange twilight, buried beneath thick toxic clouds that never clear, where the air itself is so dense that it moves slowly like a fluid, warping the horizon and creating a surreal, oppressive environment of heat and shadow. Beyond these suffocating greenhouse worlds, we're also discovering completely unique planets known as helium worlds. In our own solar system, the giant gas planets like Jupiter and Saturn are composed primarily of hydrogen gas, mixed with a smaller percentage of helium, which reflects the general chemical makeup of the primordial nebula from which our Sun was born. But under specific, highly unusual circumstances in the deep universe, a gas giant can undergo a radical chemical transformation that leaves it composed almost entirely of helium. This strange phenomenon typically occurs when a hot Jupiter orbits exceptionally close to a highly energetic host star. The intense stellar radiation heats the planet's upper atmosphere to extreme temperatures, causing the lighter hydrogen gas to expand and rapidly escape out into space over billions of years. Because helium atoms are significantly heavier than hydrogen molecules, they are much harder to strip away, allowing them to remain behind and gradually accumulate. Over time, the planet's atmosphere becomes heavily enriched with helium, transforming the world into a massive bloated ball of pure helium gas. These planets are expected to display highly unusual cloud structures, unique atmospheric chemistry, and a soft, featureless appearance that is entirely distinct from the swirling, colourful storm bands of Jupiter, standing as an exotic testament to how stars can fundamentally alter the chemical identity of their planets. We also observe that many planetary systems do not feature a neat, orderly arrangement where rocky planets sit close to the star and gas giants stay far out in the cold. When humans first began to theoretically model how solar systems form, we naturally based all of our ideas on the structure of our own neighbourhood, assuming that small, dense, rocky planets like Earth and Mars would always develop in the warm inner regions near the star, while massive gas and ice giants like Jupiter and Neptune would form in the cold, outer reaches where volatile gases could easily condense. But the discovery of thousands of exoplanets has completely shattered this neat, predictable paradigm. We frequently find massive gas giants orbiting right next to their stars in paths that take mere days to complete, while small rocky worlds can sometimes be found orbiting far out in the freezing dark. This architectural chaos reveals that planetary systems undergo a massive amount of dynamic migration and disruption during their early, formative years. As young planets grow within the swirling disk of gas and dust surrounding a newborn star, their gravitational interactions with the disk and with one another can cause them to spiral inward or be thrown outward, completely scrambling their original positions. The orderly structure of our own solar system turns out to be just one single option among an incredibly diverse array of cosmic configurations, showing us that the history of a planetary neighbourhood is often a tale of migration, survival, and chaotic rearrangement. Furthermore, astronomers are actively developing highly advanced technology to analyse the chemical components of exoplanet atmospheres directly through starlight. It is one of the absolute greatest triumphs of modern science that we can determine what gases are floating in the air of a world that is trillions of miles away, entirely invisible to our naked eyes. This is achieved through a specialized field of study known as transmission spectroscopy. When an exoplanet passes directly in front of its host star during a transit event, the vast majority of the starlight is completely blocked by the solid body of the planet. However, a tiny fraction of the starlight manages to filter through the thin, transparent ring of the planet's upper atmosphere, before continuing its long journey through space toward our telescopes on Earth. Every single gas molecule, whether it is water vapour, methane, carbon dioxide or oxygen, absorbs very specific, highly distinct wavelengths of light, leaving behind a unique chemical signature or a barcode printed directly into the starlight. By breaking this filtered light down into a detailed spectrum and carefully measuring which specific colours are missing or dimmed, astronomers can reconstruct the exact chemical recipe of the alien air. This technique allows us to peer across the vast cosmic void and understand the environments of distant worlds, searching for the telltale signs of clouds, weather patterns, and potentially even the chemical footprints of living organisms. Through these atmospheric studies, we are finding clear evidence of water vapour floating in the skies of multiple distant exoplanets. Water is universally recognised as one of the most critical ingredients for the emergence and long-term survival of life, acting as a powerful solvent that enables complex biochemical reactions to take place. Finding signs of water in the atmospheres of worlds located light-years away is an incredibly profound milestone in our ongoing search for life beyond Earth. Astronomers have successfully detected the distinct spectral signature of water vapour in the air of several different types of planets, ranging from massive, scorching hot Jupiters to more temperate, rocky super-Earths. In the case of hot gas giants, This water exists as a superheated gas mixed into a churning cauldron of vaporized rock and alkali metals, where it can never condense into rain. But on smaller, cooler worlds that reside within or near their star's habitable zone, the presence of atmospheric water vapor hints at a much more familiar environment, suggesting the potential existence of active water cycles, moving clouds, and liquid oceans resting beneath the air. Every single time we detect the familiar barcode of water in a far-off spectrum, it brings us one step closer to finding a world that truly mirrors our own, transforming the cold, alien void into a universe that feels a little more familiar and welcoming. In addition to water, scientists are also actively searching for biosignatures, which are specific combinations of atmospheric gases that could reveal the presence of active biological life. On our own planet Earth, the chemical composition of the atmosphere is profoundly altered by the continuous activity of living organisms. If all life on Earth were to suddenly vanish tomorrow, our air would rapidly change. The abundant oxygen would react with surface rocks and disappear, and gases like methane would quickly break down, leaving behind a completely different chemical balance. Therefore, when astronomers look at a distant exoplanet through their telescopes, they are not just looking for a single isolated gas like oxygen, but rather for a state of chemical disequilibrium, the simultaneous presence of gases that should normally destroy one another unless something is actively and continuously producing them. For example, finding a world with an atmosphere that holds high amounts of both oxygen and methane at the same time would be an incredibly strong indicator of life, as these two gases naturally react to form water and carbon dioxide. Detecting such a combination would suggest that an active global biosphere is operating on the surface, pumping out gases and fundamentally reshaping the planet's environment. The search for these subtle chemical signatures is a slow, incredibly meticulous process that requires our absolute most powerful space observances, but it represents our best hope for answering the ultimate human question of whether we are truly alone in the dark. Furthermore, we are uncovering the fascinating reality that certain worlds may feature active ice volcanoes or cryovolcanoes, which completely challenge our traditional understanding of geological activity. For a long time, humanity associated volcanic eruptions exclusively with blistering heat, glowing rivers of molten rock, and vents spewing white-hot ash from a planet's deep, burning interior. But across the colder, distant expanses of the deep universe, geological activity can take on an entirely different, wonderfully frozen expression. On these icy exoplanets and distant moons, the internal heat sources are not intense enough to melt silicate rock, but they are more than powerful enough to melt volatile ices. Instead of molten lava, these unique volcanoes erupt with a slushy, pressurized mixture of liquid water, ammonia, methane, and other volatile chemical compounds. When internal pressures build up deep beneath the heavy ice crust, these cold liquids are violently forced upward, erupting into the freezing air or direct vacuum of space, where they instantaneously freeze, snow back down, and gradually build up massive mountain structures made entirely of hardened ice. This incredible process shows that even the coldest, most far-flung worlds in the cosmos can remain geologically alive, actively reshaping their surfaces and transferring chemical materials from deep underground storage directly into their outer environments. Deep beneath these thick frozen crusts, massive subsurface oceans might remain completely liquid for billions of years, protected from the absolute freeze of deep space. When we view these icy worlds from the outside, they appear as completely still, silent, and dead balls of white ice drifting through the cosmic dark. But the deceptive surface crust, which can stretch down for dozens of miles, acts as an incredibly efficient thermal blanket that seals away a world of activity underneath. The water trapped in these deep underground layers is continuously kept warm and liquid by a combination of residual formation heat, radioactive decay within the planet's rocky core, and the powerful, non-stop gravitational squeezing from nearby companion worlds. These hidden seas are entirely sealed away from starlight, existing in an environment of absolute unchanging darkness under crushing structural weight. Yet, they possess all of the fundamental components necessary for complex chemistry to thrive, including liquid water, organic molecules, and hydrothermal vents on the seafloor that can pump out vital energy. These subterranean oceans represent one of the most exciting frontiers in modern astronomy, expanding our definition of habitability by proving that a world can be completely frozen and hostile on its outer surface, while cradling a warm, fluid, and potentially life-bearing environment deep inside. In stark contrast to these dark, hidden oceans, some exoplanets are situated in the quietest, most isolated corners of our vast galaxy. The Milky Way is a place of immense non-stop motion and dense stellar crowding, particularly near its brilliant central bulge and along its sweeping star-forming spiral arms. But as you travel farther outward, toward the very edges of the galactic disk, the stars begin to thin out dramatically, and the space between them widens into an immense, quiet expanse of solitude. The planets that form around the lonely stars in these galactic suburbs experience a remarkably peaceful, unchanging existence. Because they reside far away from the chaotic centers of stellar activity, they are almost never subjected to close encounters with passing stars that could violently disrupt their orbits, nor are they exposed to the devastating radiation blasts of nearby supernova explosions. This long-term environmental stability allows these far-flung worlds to maintain perfectly predictable, smooth, and gentle orbits for many billions of years without interruption. For any life that might potentially emerge on such a planet, the passage of time is a steady, uninterrupted river, providing a secure and long-lasting cosmic shelter where biological evolution can unfold at a slow, gradual pace under the dim, quiet light of a solitary sun. Conversely, other exoplanets speed through incredibly chaotic, densely crowded starfields where survival is a daily struggle against gravitational disruption. In the dense central regions of the galaxy, or inside massive globular clusters that pack hundreds of thousands of stars into a relatively tiny pocket of space, the night sky of a planet would be a dazzling, ever-shifting ballroom of fire and light. From the surface of such a world, multiple nearby suns would shine with incredible brightness, completely banishing the concept of true night and keeping the environment in a state of perpetual illumination. However, this magnificent visual beauty comes with an immense amount of cosmic danger. With stars continuously passing close to one another, the competing gravitational forces are constantly pulling and tugging at the planetary systems, frequently warping orbits, sliding worlds into highly eccentric paths, or completely tearing planets away from their parent suns to become lonely wanderers. Furthermore, the high density of massive stars means the risk of being blasted by a catastrophic supernova or an intense gamma-ray burst is exponentially higher. These planets live on a knife's edge of chaos, dodging structural ruin with every single orbit, demonstrating that the cosmic environment a solar system is born into plays a massive role in determining its ultimate fate. Looking into the most extreme graveyards of the universe, astronomers have successfully located planets orbiting around rapidly spinning pulsars. Pulsars are the hyperdense, collapsed cores of massive stars that ended their active lives in spectacular, violent supernova explosions. These exotic objects possess a mass greater than our Sun packed into a sphere the size of a city, spinning on their axes dozens or even hundreds of times every single second, while blasting out intensely narrow, highly destructive beams of radiation from their magnetic poles like cosmic lighthouses. For a long time, scientists completely assumed that it was absolutely impossible for any planet to survive the apocalyptic explosion of a supernova, believing that any nearby worlds would be instantly vaporized or flung out into deep space. Yet, against all expectations, the very first confirmed exoplanets ever discovered in human history were found orbiting the pulsar PSR B1257+12. These haunting ghost worlds orbit a dead stellar remnant, continuously bathed in an intense, crackling field of high-energy radiation and subatomic particles instead of warm, natural sunlight. Their exact origins remain a subject of deep scientific debate. They may be miraculous survivors that somehow endured the star's death, or they may have formed afterward from the fallback debris that circled the pulsar. They stand as a profound testament to the resilience of planetary formation, proving that worlds can emerge even in the wake of total stellar destruction. In addition to surviving pulsar environments, some resilient planets appear to have successfully endured the cataclysmic explosions of nearby supernovas within binary star systems. When a massive star reaches the absolute end of its nuclear life cycle and detonates as a supernova, it releases an unimaginable wave of energy, hot plasma, and heavy elements that can instantly strip away the atmospheres and incinerate the surfaces of any planets residing in the immediate neighbourhood. However, if a planet is orbiting a companion star at a sufficiently safe distance, or if its own mass and magnetic shield are strong enough, it can manage to survive the initial blast wave, remaining anchored in its orbit even as its sky is permanently set on fire. Astronomers have discovered the chemical fingerprints of these cosmic catastrophes by analysing the atmospheres of certain white dwarfs and surviving companion stars, finding high concentrations of heavy elements like iron, calcium and silicon that likely represent the pulverized, vaporized remains of sister planets that were destroyed during the blast. Any world that successfully lives through a star's final, violent breath carries the permanent, deeply seared imprint of that catastrophe, existing as a scarred, radically transformed survivor that continues to trace its silent path around a collapsed core. Furthermore, we're discovering that many exoplanets possess atmospheres that are extraordinarily rich in exotic, unfamiliar gases that create entirely unique chemical environments. On Earth, we are thoroughly accustomed to a stable, life-supporting atmosphere composed almost entirely of nitrogen and oxygen, with small traces of water vapour and carbon dioxide shaping our weather. But across the wider galaxy, the chemical recipes for planetary air are vastly more diverse and strange. On giant, superheated gas worlds that orbit close to their stars, the atmospheric chemistry becomes a churning, hyperheated cauldron where elements that are traditionally solid on Earth exist entirely as gases. Scientists have detected the clear spectral signatures of methane, carbon monoxide, vaporized sodium, potassium, and even titanium oxide drifting through the upper atmospheric layers of these worlds. These exotic gases fundamentally alter the planet's physical appearance, determining how it absorbs, scatters, or reflects starlight, and shaping weather systems that are driven by unfamiliar physics. Some of these atmospheres are highly transparent and blisteringly hot, while others are murky, toxic, and suffocating, serving as a powerful reminder that the air we breathe on Earth is just one single, rare variation in a vast cosmic spectrum of atmospheric compositions. Through these advanced atmospheric observations, we're finding that the intense heat on close-in planets can generate permanent jet streams that never shift or slow down. On a rapidly rotating world like Earth, our atmospheric winds are driven by the uneven heating of the equator and the poles, combined with the planet's spin, which creates shifting weather patterns, meandering jet streams, and seasonal storms. But on a hot Jupiter that is tidally locked to its parent star, the environmental drivers are completely constant and extreme. With one hemisphere permanently baking under a relentless stellar fire, and the other frozen in absolute darkness, an immense, unchanging temperature imbalance is established across the globe. To redistribute this staggering amount of thermal energy, the planet's atmosphere develops a colossal, planet-girdling jet stream that roars around the equator at thousands of miles per hour, far exceeding the speed of sound. This permanent wind system acts like a massive conveyor belt, continuously sweeping superheated gas from the day side over to the night side, creating a highly efficient global heat transfer mechanism. This relentless atmospheric motion ensures that the brightest, hottest point on the planet is often shifted significantly away from the substellar point where the starlight hits directly, leaving a clear, measurable imprint on the world's thermal profile that we can read from light years away. In some truly dramatic instances, these fierce, ultra-high-speed winds are powerful enough to carry vaporized metals and minerals across the planet's entire atmosphere, creating surreal metal-driven weather cycles. Imagine an environment where the clouds floating overhead are not made of gentle water droplets, but are instead composed of microscopic particles of liquid iron, silicate rock, or aluminum oxide suspended high in the air. As the permanent equatorial jet streams whip these metallic clouds around the globe, they pass from the blistering day side into the significantly cooler night side of the planet. This sudden drop in temperature causes the vaporized metals to rapidly condense, transforming the clouds into a heavy driving rain of molten metal that sweeps sideways across the landscape under the influence of supersonic winds. This violent, deeply alien weather cycle operates on a scale of sheer power and temperature that defies human imagination, transforming the atmosphere into a dynamic chemical factory where rock and metal are continuously cycled between gas and liquid states, rewriting our fundamental understanding of what a planet's sky can experience. Furthermore, we are observing sudden planet-wide weather events that are violently triggered by massive, unpredictable flares erupting from the host star. Planets do not exist in total isolation. They are deeply and permanently intertwined with the erratic behavior of the stars they orbit. This connection is especially volatile for worlds orbiting active red dwarfs or young, unstable stars that are prone to unleashing colossal stellar flares. When one of these mega flares erupts, it blasts the nearby planet with a massive instantaneous wave of X-rays, ultraviolet radiation, and high-energy charged particles. This sudden surge of energy strikes the planet's upper atmosphere like a physical blow, instantly heating the gas layers, triggering wild chemical chain reactions, and generating immense thermal shocks. Within a matter of hours, these shocks can generate violent planet-wide storms, driving fierce winds that warp existing cloud formations and rapidly redistribute heat across the entire globe. These flare-driven weather systems operate entirely outside the rules of traditional meteorology, demonstrating how an active star can directly reach across the vacuum of space to violently sculpt, disrupt, and govern the immediate environment of its planets. As we continue to catalogue this incredible diversity, astronomers are finding many Neptunes, which are worlds that are small in mass but heavily swollen with vast envelopes of gas. Within our own familiar solar system, we have a clear, distinct gap between small rocky planets like Earth and massive ice giants like Neptune, leaving us with no local examples of worlds that sit comfortably in between. But as we peer out into the wider galaxy, we are discovering that this intermediate size range is actually incredibly populated. These mini Neptunes represent a highly curious and common class of exoplanet, typically possessing a solid, heavy core made of rock and water ice that is completely surrounded by a deep, dense, and swollen blanket of hydrogen and helium gas. Because they lack a solid surface and are wrapped in such a thick atmospheric shroud, the environmental conditions inside them are deeply mysterious. Underneath the upper cloud layers, the atmospheric pressure rises rapidly, potentially transforming the gas into a hot, boiling global ocean of supercritical water or fluid gas that blurs the line between sea and sky. They fill a major evolutionary gap in our planetary models, proving that nature frequently creates worlds that are completely alien to our local experience, making up a significant portion of the galactic population. In fact, some of these exoplanets are so incredibly inflated by their host star's intense radiation that they are described as being puffed up like giant balloons. These puffy planets, or hot Saturns, possess a remarkably large physical diameter, but an exceptionally low total mass, resulting in an overall density that is incredibly sparse. One of the most famous examples is the bloated world WASP-17b, which boasts a physical size that is roughly twice as wide as Jupiter, yet contains only a small fraction of Jupiter's actual weight. This extreme balloon-like structure is the direct result of the planet's tight, blistering orbit around its parent star. As the world absorbs an immense, non-stop torrent of stellar energy, the intense heat penetrates deep into its outer gas layers, causing the molecules to break apart, expand violently, and swell outward into space. If you could somehow transport one of these ultra-low density worlds to our solar system and drop it into a colossal ocean, it would easily float on the surface like a piece of cork. Their highly elastic, unstable structures are continuously stretched, shaped, and slowly stripped away by the unrelenting starlight, providing a vivid display of how a star's energy can fundamentally inflate and reshape the physical dimensions of a giant world. Looking at the dynamics of rotation, we have discovered that there are unique exoplanets with days that are actually significantly longer than their years. For anyone living on Earth, the concept of a single day, the time it takes for the planet to complete one full spin on its axis, is a brief, rapid event compared to the length of a year, which tracks our long journey around the Sun. But across the galaxy, specific gravitational forces can completely scramble this fundamental relationship. When a planet forms or migrates into a path that sits exceptionally close to its parent star, the star's immense tidal gravity acts like a powerful brake, slowly catching the planet's rotation and locking its spin into a highly synchronized rhythm. In some specific scenarios involving highly elliptical or complex orbits, this tidal braking can slow the planet's rotation down so dramatically that it takes hundreds of Earth days to complete just one single spin. Meanwhile, because it's positioned so close to the star, its orbital speed is incredibly fast, allowing it to complete a full revolution around the Sun in just a fraction of that time. On these surreal worlds, the planet literally finishes a complete annual journey through space before it even manages to turn around once on its axis, completely upending our traditional human definitions of time, calendars, and seasons. On these highly synchronized, close-in worlds, the planet is usually tidally locked, creating a permanent environmental division where one hemisphere is frozen in eternal darkness, while the other burns under an unending noon. Because the planet's rotation period has been slowed down until it perfectly matches its orbital period, it circles its star while continuously presenting the exact same face to the stellar fire, much like our moon does as it circles Earth. This creates a deeply dramatic, permanent geographical split across the globe. On the day side, the Sun looms colossal and completely motionless in the sky, never rising or setting, but rather beating down with a relentless non-stop glare that bakes the landscape into a scorched desert or a sea of molten lava. Meanwhile, the night side is turned toward the freezing void of open space forever, locked in a state of absolute pitch-black darkness, where temperatures plummet toward absolute zero, allowing gases to condense and freeze onto the ground as thick layers of exotic ice. This unchanging, eternal division creates a hauntingly beautiful and extreme world, where time stands completely still and the sky is forever divided between fire and ice. Furthermore, some distant worlds may be completely covered in thick, murky, and hazy skies that draw an impenetrable veil over the entire planet. When we imagine travelling to alien worlds, our minds naturally picture clear, pristine skies that offer breathtaking panoramic views of alien mountain ranges and distant star fields. But the atmospheric reality for many exoplanets is far more secretive and shrouded. Across the galaxy, many worlds are wrapped in deep, dense layers of global haze that completely block incoming starlight and obscure everything resting below from view. These extensive hazes are typically created by photochemical smog, which forms when ultraviolet light from the host star strikes the upper atmosphere, triggering complex chemical reactions among hydrocarbons like methane and nitrogen. This process builds up a thick, uniform layer of organic soot particles suspended high in the air, much like the golden fog that completely blankets Saturn's moon Titan in our own solar system. From open space, these hazy planets appear as completely muted, featureless spheres of colour, hiding their true identity. But beneath that silent, unchanging veil, immense winds may scream, deep global oceans might churn, and complex geological landscapes wait in total shadow, remaining completely tantalizing secrets that we can only hope to uncover as our scientific tools grow sharper. Furthermore, we're uncovering the incredible fact that some distant exoplanets might possess vast global rings composed almost completely of dark carbon dust and organic soot, rather than bright water ice. When we look at the beautiful ring systems inside our own solar system, such as the magnificent structures encircling Saturn, Uranus, or Neptune, our eyes are naturally drawn to their bright reflective qualities. This brilliance occurs because those rings are predominantly made of highly reflective water ice particles that scatter sunlight efficiently like tiny mirrors. But in warmer, more chemically complex regions of the deep universe, a planet can capture a completely different kind of debris field. On worlds that form near carbon-rich stars or experience intense atmospheric erosion from photochemical smog, the surrounding rings can be constructed out of microscopic carbon fragments, tar-like polymers, and complex hydrocarbons. These dark organic rings absorb nearly all incoming starlight, making them incredibly faint, shadowy, and exceptionally difficult for traditional telescopes to spot directly from Earth. They drift through space as silent, nearly invisible halos, wrapping their host worlds in a subtle, dark embrace that can only be detected when they pass directly in front of a background star, momentarily filtering its light through a fine mesh of organic cosmic dust. Deep within these massive ring structures, small shepherd moons are continuously working to maintain the clean, sharp boundaries of the individual bands. A planetary ring system is not a single, solid sheet of material. It is a highly fluid, ever-shifting collection of billions of individual particles that are constantly colliding and drifting under the influence of gravity. Without an organizing force to keep them in check, these fine particles would naturally scatter outward into open space over time, causing the rings to gradually widen, thin out, and completely disappear. To prevent this dispersion, nature utilizes small, rocky satellites that orbit directly inside or right along the outer edges of the ring gaps. These shepherd moons act as literal gravitational guardians, using their tiny but precise gravitational pull to herd the stray ring particles back into line. As a shepherd moon travels along its path, it pulls particles closer to its body, either accelerating them into higher orbits or slowing them down into lower positions, effectively carving out crisp, empty gaps and keeping the ring edges perfectly defined. This beautiful gravitational balancing act creates a complex harmonic structure, turning a loose cloud of space debris into an elegant, highly structured work of cosmic art that can endure for hundreds of millions of years. In addition to these dark rings, we are discovering that certain exoplanets possess surfaces that are completely covered by vast, shimmering sheets of dry ice instead of water ice. On Earth, we are thoroughly familiar with water freezing into ice and snow when the temperature drops during winter, shaping our glaciers and polar ice caps. But on distant worlds that form far away from their host suns and possess atmospheres that are intensely rich in carbon dioxide, the freezing process takes on an entirely different chemical identity. When the surface temperatures on these far-flung planets drop below -108 degrees Fahrenheit, the carbon dioxide gas in the air begins to freeze directly into a solid state, skipping the liquid phase entirely through a process known as deposition. This creates colossal polar caps and sprawling plains of solid dry ice that blanket the planet's landscape for thousands of miles. During the long, cold winters, this dry ice snow falls softly from carbon-rich clouds, building up deep, powdery drifts that shimmer with a strange, glassy brilliance under the dim light of a distant star. When the seasons slowly shift and the environment warms slightly, these dry ice sheets sublimate directly back into gas, creating immense atmospheric pressure waves and driving low-altitude winds that sweep across the frozen plains in complete silence. Turning our minds to even more extreme environments, astronomers have successfully identified planets where the surface rocks are completely vaporized by intense heat and then fall back down as stone rain. On worlds that orbit exceptionally close to their parent stars, such as the blistering rocky planet Corot 7b, the dayside is subjected to a relentless, non-stop torrent of stellar radiation that keeps the surface in a permanent state of liquid meltdown. The temperatures on this scorched hemisphere soar well above 4,000 degrees Fahrenheit, which is hot enough to melt and boil solid silicate rocks, iron, and magnesium. This extreme thermal energy causes the molten rock to actively evaporate, transforming solid stone into a dense mineral-rich vapor that rises high into the planet's lower atmosphere. As the powerful atmospheric currents carry this rocky vapor toward the cooler boundaries of the twilight zone or over to the frozen night side, the temperature drops rapidly. This sudden cooling forces the vaporized minerals to condense back into solid form, generating unique weather systems where pebbles, sand, and tiny rock fragments rain down from the sky, clattering against the molten lava oceans below. It is a violent, deeply alien geological cycle that constantly vaporizes and reconstitutes the very ground itself, showing us that rock can behave exactly like water under the right cosmic conditions. Furthermore, we are finding that a large number of these superheated rocky worlds may feature immense global oceans of churning magma that span across an entire hemisphere. When a planet is positioned so incredibly close to its host sun, the intense gravitational tides pull violently at its internal structure, stretching and squeezing the world with every single orbit. This relentless tidal flexing generates a massive amount of internal friction and geothermal heat deep within the core and mantle, matching the blisteringly hot starlight striking the exterior surface. This combined assault ensures that the planet's crust can never cool down or solidify on its dayside, leaving behind a colossal, open sea of liquid magma that bubbles and churns under a toxic sky. These magma oceans can be hundreds of miles deep, featuring immense currents of molten basalt and silicate rock that circulate heat around the planet's dayside. The surface of these liquid stone seas is constantly shifting, cracking open to reveal blinding white-hot currents beneath, while dark rafts of cooling rock drift across the molten expanse like transient islands before being pulled down and remelted into the deep, fiery interior. In sharp contrast to those blisteringly hot lava worlds, some exoplanets are wrapped in atmospheres that are so incredibly cold that methane gas condenses into liquid form and falls as rain. These frigid worlds share many of the same unique environmental characteristics as Saturn's largest moon, Titan, but on a much vaster planetary scale. Imagine a massive world situated far beyond the warm reach of its host star, where the ambient temperatures permanently hover around -290 degrees Fahrenheit. At these extreme lows, water ice becomes as hard and rigid as solid granite, completely incapable of melting or flowing. However, volatile hydrocarbons like methane and ethane, which exist purely as gases in the warm environment of Earth, behave exactly like liquids on these frozen planets. The methane gas in the atmosphere condenses to form deep orange clouds that drift slowly across the hazy sky, eventually dropping liquid methane rain onto the landscape below. This cold precipitation feeds intricate networks of flowing rivers and carves deep valleys into the hard water ice bedrock, eventually collecting in massive smooth-surfaced lakes and seas of liquid fuel that glisten quietly in the faint starlight, presenting a perfectly mirror-like landscape of liquid gas and frozen ice. Beyond these cold hydrocarbon worlds, we're also discovering completely unique planets known as carbon planets. In our own solar system, the rocky planets like Earth, Mars, and Venus are classified as silicate planets, meaning their internal geology and surface rocks are composed primarily of silicon, oxygen, and iron, with carbon existing as a relatively minor chemical trace. But in regions of the galaxy where the raw material disk surrounding a newborn star is uniquely rich in carbon and heavily depleted of oxygen, the planetary building blocks change entirely. On a carbon planet, the internal mantle is composed largely of carbon compounds, featuring massive layers of graphite, carbides, and deep subterranean regions of pure crystalline diamond forged under crushing structural pressure. The surface of such a world would look completely alien, featuring jagged mountain ranges made of black coal-like material, sweeping dunes of fine diamond dust, and vast plains crusted over with dark tars and glistening hydrocarbons. The rivers and lakes on a carbon planet would not consist of water, but rather of liquid oil and complex chemical compounds, creating a dark, murky, and highly stable world that operates on a completely different set of geological rules than our own rocky home. We also observe that many planets do not stay in the exact same orbital paths where they were originally born, but instead undergo massive inward or outward migrations throughout their long lifetimes. When astronomers first began to detect giant gas planets orbiting blisteringly close to their stars, the famous hot Jupiters, it completely contradicted our traditional models of planet formation, which stated that gas giants could only develop in the cold outer regions of a solar system where volatile gases could accumulate. The solution to this paradox lies in the dynamic science of planetary migration. During the early, chaotic infancy of a solar system, a young planet is surrounded by a dense, swirling disk of leftover gas and dust. As the planet travels through this material, its gravity creates ripples and waves in the disk, which pull back on the planet, draining its orbital energy and causing it to slowly spiral inward toward the star over millions of years. Alternatively, gravitational close encounters between multiple massive planets can result in one world being violently thrown into a tight, extreme orbit, while its siblings are cast out into the deep freeze of interstellar space, proving that the positions of planets are never permanently fixed. Furthermore, astronomers are finding that this long-term planetary migration can frequently slide planets directly into orbital resonances with one another, creating highly stable and beautifully synchronized celestial clocks. When multiple planets orbit a single star, their individual gravitational fields are constantly tugging at one another with every close pass. Over billions of years, these repeated interactions can gently guide the planets into a highly coordinated mathematical harmony known as a resonant chain. In a resonant system, the orbital periods of the planets form perfect, simple ratios with one another. For instance, for every 3 times the innermost planet completes a full circuit around the star, the second planet might finish exactly 2 orbits, and the third planet might finish exactly 1. This precise timing means the planets regularly line up in the exact same positions, balancing their mutual gravitational pulls and protecting the system from chaotic disruptions. We have discovered several multi-planet systems, such as HD 1167, that feature long, unbroken chains of resonant harmony, turning the entire planetary neighborhood into a perfectly synchronized cosmic clock that has been ticking in complete silence since the dawn of time. Through these delicate gravitational harmonies, we are learning that a planet's orbital shape can be continuously altered from a perfect circle into a highly elongated ellipse over time. While we often picture planets travelling along neat, perfectly round tracks around their suns, the reality is that gravity is constantly warping these paths into more eccentric shapes. When a planet experiences regular gravitational nudges from an outer companion world or a passing star, its orbit can gradually stretch out, causing it to travel along a long oval-shaped trajectory. A planet on a highly eccentric orbit experiences wild, extreme shifts in its daily environment throughout its year. When it reaches periastron, the point in its orbit closest to the star, it skims incredibly near the stellar fire, experiencing a sudden, intense summer where the atmosphere bakes and cloud layers vaporize rapidly. As it swings back out toward Apastron, the farthest point in its orbit, it retreats deep into the freezing dark, experiencing a long, silent winter where gases cool, clouds condense, and temperatures plummet dramatically. These eccentric worlds live in a constant state of environmental whiplash, transitioning between a blistering furnace and an icy wasteland with every single revolution. In addition to these extreme climate shifts, highly eccentric orbits can generate immense internal friction within a planet through a process known as tidal dissipation. As an eccentric planet races along its oval path, the distance between it and its host star is constantly and rapidly changing. When the planet skims close to the star, the immense stellar gravity pulls at the world with maximum strength, causing its physical body to stretch and distort into a subtle teardrop shape. As the planet retreats back out into deep space, the gravitational pull weakens significantly, allowing the world to relax back into a more spherical shape. This continuous, non-stop stretching and relaxing occurs with every single orbit, creating an immense amount of internal friction deep within the planet's mantle and core. This tidal friction acts like a powerful internal heater, pumping vast amounts of thermal energy directly into the world's interior, keeping its core molten, driving intense volcanic activity, and potentially melting subsurface oceans even on planets that spend most of their time far out in the freezing cold, proving that a star can warm its planets from the inside out through gravity alone. Furthermore, we are uncovering evidence that certain far-off worlds can actually possess vast global oceans of liquid ammonia and liquid water mixed together, which entirely alters the physical behavior of their deep hydrological cycles. In our local solar neighborhood, we traditionally recognize water as freezing solid at 32 degrees Fahrenheit, creating rigid sheets of ice that lock planetary landscapes into an unchanging stillness. But in the colder, more distant expanses of the galaxy, the introduction of a simple chemical like ammonia completely changes the cosmic rules. Ammonia acts as an exceptionally powerful natural liquid antifreeze. When an alien world possesses an abundant supply of both water and ammonia within its chemical makeup, the two substances mix thoroughly, drastically lowering the overall freezing point of the liquid solution down to nearly -100 degrees Fahrenheit. This allows immense subterranean or surface seas to stay perfectly fluid and active at temperatures that would easily freeze a normal earthly ocean solid in a matter of seconds. These fluid ammonia-water oceans can generate highly unusual, slow-moving currents that transfer heat across the planet, eroding frozen bedrock made of hardened gases and creating unique chemical networks that flow through the absolute dark. It stands as a profound reminder that nature can easily build fluid, dynamic planetary environments using alternative chemical recipes, keeping worlds alive and moving in places where we once expected to find nothing but frozen silence. Deep within these massive chemical oceans, the extreme physical pressure can also compress the liquid molecules into unique, exotic phases of matter that defy our daily observations. On Earth, we are thoroughly accustomed to matter existing in three clear distinct states: solid, liquid, and gas. But when you travel deep beneath the heavy cloud decks and immense ocean layers of a giant exoplanet, the sheer structural weight of the material above climbs to unbelievable limits. Under the crushing pressure of hundreds of miles of ocean, liquid molecules are squeezed so tightly together that they can no longer slide past one another freely, yet the internal geothermal heat prevents them from locking into a standard crystalline solid. This creates a highly unusual state of matter known as a supercritical fluid, where the distinct boundary line separating a gas from a liquid vanishes entirely. The material becomes an incredibly dense, thick fog that behaves simultaneously like a heavy gas and a fluid liquid, possessing the ability to dissolve minerals like a liquid while diffusing through rock layers like a gas. This exotic fluid layer forms a massive transition zone deep inside the planet, connecting the upper atmosphere to the rocky core and serving as a major chemical engine that continually shapes the world's internal temperature and magnetic alignment over billions of years. In addition to these supercritical fluid layers, we're discovering that certain exoplanets possess physical orientations that cause them to spin completely on their sides as they orbit their host suns. When we observe the planets inside our own solar system, the vast majority of them rotate relatively upright, like spinning tops turning gracefully on a flat table. Our own planet Earth possesses a modest axial tilt of 23 degrees, which is just enough to give us our gentle, changing seasons throughout the year. But out in the wider galaxy, severe gravitational disruptions can tilt a world completely over. Imagine a planet where the axial tilt reaches nearly 90 degrees, leaving its poles pointing directly toward the stellar fire. This unique orientation creates a truly extreme planetary environment. During one half of its long annual journey around the star, one entire hemisphere is locked in a state of continuous, non-stop daylight that bakes the landscape under a relentless sun that never sets, but instead traces a tight circular spiral directly overhead. Meanwhile, the opposing hemisphere is cast into an eternal, freezing winter night, facing the absolute dark of open space for decades at a time. This extreme arrangement generates colossal atmospheric temperature differences, driving fierce, planet-wide winds that scream across the twilight boundary to balance the global climate, demonstrating how a simple shift in a planet's physical orientation can completely transform its entire meteorological identity. Turning our attention back toward the search for Earth-like worlds, astronomers are focusing their most advanced instruments on locating planets that orbit stable, long-lived yellow dwarf stars like our own Sun. While cool red dwarfs are far more numerous across the galaxy, their tendency to unleash violent stellar flares and tidally lock their close-in planets presents major hurdles for the long-term survival of complex atmospheres. Yellow dwarf stars, by contrast, offer a much more balanced and stable stellar environment. They emit a steady, predictable stream of light and heat, and their habitable zones are positioned far enough away from the stellar surface that any planet residing there can maintain a rapid, healthy daily rotation. This rapid spin helps distribute thermal energy evenly across the entire globe, preventing extreme temperature dead zones and helping to generate a strong protective global magnetic field. These solar systems represent our absolute best chance for finding an environment that truly mirrors the conditions we enjoy on Earth, providing a calm, well-regulated stellar harbour where liquid water can pool safely on a rocky surface. Clouds can drift through a familiar sky, and biological evolution can unfold over many billions of years in complete safety. Furthermore, we're finding that the presence of a massive outer gas giant within a solar system can play an incredibly critical role in protecting inner rocky planets from devastating cosmic impacts. Within our own neighbourhood, the immense gravity of Jupiter acts like a giant cosmic shield or a planetary vacuum cleaner. As dangerous comets and rocky asteroids rush inward from the outer edges of the solar system, Jupiter's massive gravitational field routinely intercepts them, either swallowing them outright or violently slinging them entirely out into deep space, far away from the inner planets. When astronomers study distant exoplanetary systems, they look carefully for this specific architectural arrangement. A solar system that possesses a large, stable gas giant operating in a wide outer orbit can create a highly secure, peaceful environment for any smaller rocky worlds nestled closer to the star. By continuously sweeping away destructive debris over billions of years, The outer giant drastically reduces the overall frequency of catastrophic asteroid impacts, allowing any emerging biosphere on the inner planets to evolve steadily without being periodically wiped out by global extinction events, showing us that the habitability of a world is often governed by the actions of its planetary neighbours. In sharp contrast to those secure, well-protected solar neighbourhoods, some rocky planets are completely exposed to a continuous, non-stop bombardment of space debris because they lack any outer guardians. In systems where no giant planets formed, or where the gas giants migrated into tight inner orbits, the outer asteroid and comet belts remain highly unstable and chaotic. Without a massive gravitational anchor to clear the pathways, countless rocky fragments and icy bodies are constantly jostled out of their positions, raining down into the inner system in a relentless cosmic assault. For a rocky planet trapped in this environment, the surface is a scarred, heavily cratered wasteland that is continually reshaped by cataclysmic impacts. Every few million years, a massive asteroid strikes the crust, releasing enough thermal energy to vaporize oceans, set the atmosphere on fire, and completely melt the surface rocks back into a global sea of lava. These unstable systems are incredibly hostile to the long-term survival of an atmosphere or liquid water, serving as a powerful reminder of how incredibly fortunate we are to live in a solar system that possesses an orderly structure, where gravity works to preserve life rather than destroy it. Beyond these chaotic bombardment zones, we're also discovering completely unique planets, known as ocean-bearing super-Earths, that possess no solid land whatsoever, but are instead wrapped in a global shroud of deep water. These worlds sit in a highly tantalizing size range, being several times heavier than Earth, but retaining a dense, rocky interior beneath their immense aquatic layers. Unlike the deep water worlds that are completely gaseous or icy, these planets feature a true liquid ocean that sits directly in contact with a solid, rocky mantle on the seafloor. This direct contact is incredibly significant for chemistry, as it allows vital minerals, salts, and volcanic nutrients to dissolve directly into the water from hydrothermal vents, creating a rich chemical soup that is highly favourable for the emergence of living organisms. The skies above these global seas are likely thick with heavy water vapour clouds, creating an unchanging warm humidity that blankets the entire planet. With no mountain ranges to break the wind and no continents to deflect the currents, immense global tides roll across the endless waters in a steady rhythmic cycle, turning the entire planet into a vast, self-regulating aquatic ecosystem that turns quietly in the starlight. We also observe that many stars do not exist in total isolation, but are born as twins or triplets within massive stellar nurseries, which heavily complicates the early structural dynamics of planet formation. When a colossal cloud of interstellar gas and dust begins to collapse under gravity to form new stars, it frequently fragments into multiple distinct pockets, resulting in the creation of binary or multiple star systems. In these crowded environments, the raw material disks surrounding the young stars are continuously warped, tilted, and shredded by the competing gravitational pulls of the neighbouring suns. For a planet trying to grow within this swirling chaos, the pathway to survival is incredibly narrow. Material can be pulled away entirely or forced into highly unstable orbits that cause growing protoplanets to violently collide and smash one another to pieces. Yet, our telescopes continuously show that planets routinely conquer these difficult odds, managing to settle into stable long-term orbits even within the most tangled gravitational fields, proving that the drive for matter to organize into worlds is one of the most resilient and fundamental forces operating across the deep universe. Furthermore, astronomers are finding that the specific color of starlight emitted by a host star can fundamentally dictate the colors of any potential vegetation or plant-like organisms evolving on a planet's surface. On Earth, our plants appear predominantly green because they utilize a specialized pigment called chlorophyll to absorb light from our yellow sun, while which peaks in the blue and red parts of the spectrum while reflecting green light away. But when we look at planets orbiting different classes of stars, the rules of photosynthesis must adapt to the available light. A planet orbiting a cool red dwarf star receives starlight that is heavily weighted toward the low-energy infrared and red regions of the spectrum. To capture enough energy to drive chemical reactions, alien plants on such a world would need to absorb every single photon of visible light possible, causing them to develop pigments that appear completely black or deep purple to human eyes. Conversely, a planet orbiting a bright, energetic blue star would be bathed in an abundance of high-energy ultraviolet and blue light, requiring plants to protect themselves from radiation damage by reflecting away the intense blue rays, resulting in landscapes blanketed in brilliant shades of yellow, orange, or red, turning botany into a direct reflection of stellar physics. Through these incredible insights into alien environments, we are learning to appreciate just how deeply intertwined a planet's surface conditions are with the overarching life cycle of its host star. A planet can never be understood as a completely separate, independent object. It is an active extension of the star that gave it birth and continuously sustains it with energy. As a star slowly ages over billions of years, its core temperature rises, causing it to gradually brighten and emit more heat into the surrounding space. This slow stellar evolution causes the system's habitable zone to gradually drift outward over time, slowly turning once temperate inner worlds into scorched, desiccated deserts, while warming up frozen, outer ice giants into temporary water paradises. A world that is perfectly hospitable to life today may eventually find its oceans boiling away into space tomorrow, while a cold, silent moon far out in the dark could slowly wake up and experience its own brief summer. The cosmos is a grand, unfolding narrative of change and adaptation, where planets and stars move together through time in a continuous, beautiful and silent symphony of light and shadow.